Again, these are short introductions. There is lots of information on data platforms, their resolution in time and space, and how they are used. For example, many of the things are not directly measured, like energy. We are deriving. Solar radiation can be directly measured. Outgoing long-wave radiation can be directly measured. But when we say ocean heat content, we are taking temperature and deriving a heat content and other forms of energy. We are also deriving sea level, sometimes based on temperature and salinity changes and glacier melts and so on and so forth. Okay, so just be aware that there are some things that are directly measurable. There are some things that have to be derived from other data, and some things that are just about impossible to measure. Okay, so CO2, which is the main culprit in terms of greenhouse warming and anthropogenic contribution to greenhouse increases and climate change, is something that has a long residence time. It means if you put a pulse of CO2 in the atmosphere, how long it stays around before it equilibrates or disappears. It is the residence time. It basically reservoir size, flux coming in, flux going out. There are formal definitions you can find in my oceanography course, for example. It lives a long time. It's inert and dissolves in water, of course, but it's well mixed. So if you measure it at one place, it gives you a very good sense of the hemispheric CO2 level. There are cross-hemispheric gradients because it's hard to cross the equator because the Coriolis changes sign and so on, rotational effect, etc. Sources and sinks are also different on the northern and southern hemispheres. So in the 1950s, Charles David Keeling, a student of Roger Revelle, started to measure CO2 on Mauna Loa in Hawaii. Turned out to be the most amazing data we could have ever generated in human history, other than, of course, the astrophysics stuff. So we are looking at parts per million by volume here, changing from about 320 to now approaching 420. We're increasing by about 4 ppm now. So increase in CO2 is also accelerating, which is sad because we are just about finished with COP26, 25 years of negotiations, and you can see that the CO2 is continuously increasing and shows no signs of decreasing. So the data for CO2 can be easily collected in the atmosphere accurately and precisely by measuring at a few stations, and there are a number of stations now measuring CO2, but this is not so easy for other greenhouse gases like methane and N2O, which are very small in concentration already. This is amounts to about 0.04% concentration wise, and methane and N2O are measured in parts per billion as opposed to parts per million by volume. So they are even smaller amounts, and they are very non-uniform, and they are not as well mixed. So sampling becomes a big issue as well. So carbon cycle, when we say carbon cycle, typically we are worried about energy balance in addition to other things like ocean acidification and pollution, but and of course impacts on crops and forests and temperature increase feedbacks and so on and so forth. But collecting data for carbon cycle is even more complicated when you look at the kind of calculations we need to do the carbon cycle. So this is the best estimate that usually gets put out every year by the Global Carbon Project and other organizations or coordinated international activities. So here we are looking, just don't get scared by looking at all the numbers, but just try to understand how difficult it is to get a hold of these numbers. So, and the uncertainty range tells you how difficult they are. So emissions from volcanoes, for example, over this period of 2009 to 2018 in gigatons of carbon per year. Okay, that's a unit that's most typically used. There is also something called CO2 equivalent, which we will come back to later, or gigaton CO2 instead of gigaton carbon. So you have to always make sure that you are looking at the numbers properly. Okay, so the blue arrows are anthropogenic fluxes over this period. Land up, so the green arrows are up uptake or sinks of carbon, sources of carbon, and land use change is deforestation, urbanization, etc. And ocean uptake. We said ocean takes up 93% of the energy, so there is that one. So plus is when there is atmospheric increase of the CO2, and then budget imbalance also exists. So carbon cycling in gigatons, and then stocks. So ocean, for example, has a stock of carbon. Atmosphere has a stock of carbon on which you are adding or subtracting. So you need to look at reservoir size and fluxes. So this is 9.5 gigaton carbon per year for this period, carbon per year, going from the human activities into the system. Land is taking up 3.2 by wetlands, forests, etc. Land use change, as we said, is putting out 1.5 gigaton. So what is the point? When you think of data, look at these numbers. The uptake is 120 gigatons, and the rest. So think of forests photosynthesizing and respiring. There will be two large numbers like 120 gigaton and 120 gigaton, and there is a tiny bit of carbon being sequestered, and you have to get a good handle on that. So you have to have very good data to look for these small differences in two big numbers. So ocean is taking up 90 and putting out 90 through respiration and photosynthesis and other processes, and the net uptake by the ocean is like estimated to be 2.5 gigaton carbon per year, with a range of 1.9 to 3.1. So there is a large range because of sampling issues and difficulties in measuring, etc. And these are of course estimates. Dissolved inorganic carbon, marine biota, how much standing stock there is, oceanic carbon, organic carbon, sorry, 700 gigatons. This is 38,000 gigatons of carbon. So surface sediments, coasts, rivers and lakes, soils, permafrost, which has a substantial amount, and of course coal reserves, oil reserves and gas reserves. These are massive amounts, and what we have to think about is if we burn all this, how much carbon we're going to end up putting into the atmosphere and ocean and land, and what the consequences are going to be in terms of warming, sea level rise, glacier melt, health, vegetation, crop yields, so on and so forth. Okay, so typically this is what is done in a global mean sense. So for a long time the fossil fuel, which is a very valuable commodity, is tracked very closely, and we know very well how much carbon it emits. So it's the largest contributor, and it is increasing in time with dips that are related typically to depressions, financial crises and so on and so forth. Land use change adds a little bit. So those are the sources of carbon, CO2 flux in gigaton carbon per year over time. And land use change fortunately has flattened out, but these are again estimates, so data. Ocean is increasingly taking up more because CO2 dissolves easily in the ocean, but the question is, when will ocean get saturated? If you go to my carbon cycle course, you will see that ocean carbon chemistry is quite complicated, and there are many ways in which ocean can continue to take up CO2, but eventually it's going to get saturated. But even before it is saturated, it's getting acidified, which is a big problem for corals and other shell forming animals. Okay, so that's something one has to remember. Land uptake, so there is sequestration on land into soil, vegetation and so on, so that is increased, and atmosphere is accumulating the rest of it, of course, and there are imbalances. So there is this gray line which shows that estimates, because of data limitations and other uncertainties in carbon cycle, carbon stocks and so on, there are often imbalances. Sometimes it's referred to as missing sink, but which means that to balance the known sources, we need a certain amount of CO2 to be going somewhere, the dark matter, as it were. Okay, so that's a difficult problem as well. So carbon cycle data is quite complicated, much more complicated than weather and climate data and climate change data. So weather and climate data are needed for short-term predictions, initializing the models, and so on. Climate change data is best done when it has good spatial coverage, temporal coverage, and continuity, so that we can track the changes with confidence. Okay, so just think about all the data that is needed, and we will conclude this chapter by looking at the number of data sources that exist from on land, on ocean, and by satellites. Obviously, again, not very comprehensive, but just to give you a sense of the efforts that are going on.